All right, over to you, Michael.
All right. Thank you, Vaibhav. Hello, everyone. I'm Michael Hood, a software architect with Werner Enterprises, and today I'm going to speak about the training models in Azure Machine Learning Studio. It's a specialized resource that Microsoft has created to aid in some of the more complex tasks that people have encountered with machine learning. So you don't have to be a data scientist or have a PhD to be able to do some of these things, thankfully. Or you don't even have to like be an expert inside of Python. But yeah, Microsoft has created this around the machine learning project lifecycle. It has no code and low code solutions inside of it. So go to the next thing. Yeah, just a little bit more about me. I started my enterprise work with a Shibui development group in Pensacola, and moved on from there right out of school into App River out of Gulf Breeze, Florida. They were or are rather, they were bought by Zix, a spam and web filtering company. So I got experience with spam filters there, and moved on to IBM out of Baton Rouge, and worked for several clients there for a number of years. And currently I'm working with Werner Enterprises on the Werner Edge arm. I'm very passionate about new technology and piano improvisation and writing. And my first computer was the TRS-80 Coco 2, something you would plug into a television that had 80 characters on the screen with. So what is machine learning? I'll just read through this. Machine learning is the use and development of computer systems that are able to learn and adapt without following explicit instructions by using algorithms and statistical models to analyze and draw inferences from patterns in data. It was coined in 1959 by an IBMer named Arthur Samuel. He was a pioneer in computer gaming and artificial intelligence. Machine learning differs from purely symbolic methods in the AI discipline. It came out of what was then called neural networks or perceptrons, and earlier statistical methods that had nothing to do with artificial intelligence, but they found later on that they were useful for some of the processes that they observed in nature. So with Azure Machine Learning, it's a cloud service, like I mentioned before, that it's a resource in Azure that you can use to train and manage machine learning models. And it contains no code and code first approaches. So with Azure Machine Learning, we'll create resources and verify the training pipeline for a regression model, which is a kind of model that computes a numerical value. We'll create the inference pipeline and deploy the inference pipeline as a service. You pay for the compute resources you use to train the model and host the inference pipeline and the storage for various aspects of the account. But largely, if you stop your compute resource and delete your endpoint, you should only incur a small storage fee. So if you want to retain what you've created, like some of the Jupyter notebooks or your data sets. You can delete all things, though, if you want to be free and clear from it all. So there's very little risk on it in the pay-as-you-go model. Other things that you can do besides what we're going to do today, which is a supervised regression model with the AI-related service offerings, are computer vision. That one is with the custom, that's a little bit different. The custom vision service is something you can use to extract information from images. Computer vision is a little different. Face service is something that you can use to detect and analyze faces. The form recognizer allows you to automate data extraction from like scanned receipts or paycheck stubs, or basically any form that has any common pattern for the layout. If there is a common pattern on the form, then you can rely upon the order in which it will parse. It's fairly consistent on that. So there's a lot of neat things you can do with that. Most businesses use some kind of form that requires parsing. Natural language processing, that's a resource that there are a lot of new developments with that, especially with the GPT-3 model that OpenAI has developed that Microsoft has exclusive licensing for. I'll mention that in a later slide here. But with a natural language processing service offering, you can perform sentiment analysis and key phrase extraction. Basically, like, what's the mood about text, or to identify key phrases inside of a body of text or corpus, named entity recognition, finding what we call anaphora resolution, which if you have like a pronoun it, then the system can identify what you meant by it by referring to something previously inside of the corpus of text. But that resource, the NLP one, can help with identifying those, and language detection. So yeah, I can recognize what human spoken language body of text is. With Azure Cognitive Services, it's a suite of services that's aimed at easily adding cognitive abilities to apps with an API, not necessarily with a lot of code. So the translator text service is a text-to-text translation between languages, and the speech one is a speech-to-text and text-to-speech. So there's a lot in there. Yeah, but we'll be focusing on the studio and building up something from largely from scratch. So GPT-3, I would look into that one a little bit. There's some interesting stuff that's going to come out of that. The ability to extract from body of text, like synopses, to generate text based upon pre-trained models that you can infer from it. It's a 175 billion parameter model. So a parameter in this sense is going to have a different name later on that we'll use called a feature. But a model parameter is a configuration variable that's internal to the model, and whose value can be estimated from the given data. But yeah, with this exclusive partnership that Microsoft has with OpenAI, they're starting to create preview resources and service offerings inside of Azure, and this one's going to be pretty amazing up and coming. So I would keep your eye on it if you can. Right now, I'll ask a question, and you can put your answer inside the chat, but we'll address at a later point of the presentation during the demonstration part any of the answers that people have. But just to get you thinking about some of these services that you've heard about, or I'm sure you've seen inside of the news, there are a lot of ways that you see AI crop up in apps, or sometimes you suppose that it's being used in the background. And it's very easy to say, well, I would like to use translation. Well, there's a translation app, but that's not the only way in which it could be used. One of the ways to spark innovation is to, yeah, just look at a problem and imagine the most wild thing that you could about it. Try to break the laws of physics, or whatever it is that you could improve your life in ways that you haven't already seen. But what is one way that you could use an Azure AI service to improve a solution? And this is the list again, if you guys want that as a reference. But yeah, I'll just encourage you, if you have an idea about something, and pop it inside the chat, and we'll revisit it later on. Okay, so if you're interested in getting a little bit more formal familiarity with some of these service offerings and the ML Studio, the fundamentals and the associate level of depth for certification with Microsoft are available. They don't have a 3-star expert one yet, but honestly, like, the fundamentals track will expose you to pretty much everything. The associate track goes a little bit further with implementation, but there is some implementation that you can do at the fundamentals level. You'll be able to describe at the AI 900 how AI workloads and how AI workloads work, but the fundamental principles of machine learning on Azure, features of computer vision and natural language processing and conversational AI. But yeah, with the associate level, you'll implement those things. The example that we're using after the deck is going to be able to be found inside of the AI 900 learning path. And if you haven't used any of Microsoft's learning paths yet, they're better and free than Pluralsight or Udemy or any of those other. And they're very well organized. They usually even have a way to spin up resources within the learning path itself, but I would check that out. So machine learning terms and definitions. We're going to cover some of those that are necessary. Supervised versus unsupervised. You might have heard of this before. We are going to do what is a supervised model or supervised training pipeline. Supervised means that the training data includes known label values, and we'll get what a label is. It's what we're going to predict. In unsupervised learning, the data points aren't labeled and the algorithm labels them for you by organizing the data or describing its structure and clustering them around the hidden patterns there. So there are largely two types of supervised machine learning techniques, regression and classification. And what we're doing is the linear regression form. Classification has a threshold value that it uses to, the model uses to identify something as being a part of a group. And there are some interesting modules inside of the learning path for AI 900 to show you how to do that. With unsupervised learning, clustering and association are the large two groups there, but we won't go into depth for that yet. So yeah, features. This is another term used with linear regression models and supervised learning. When you have a list of values instead of a table for like a let's say comma separated values for a series of historical data points that you want to use to predict a numerical value for. Each one of those columns is a feature, and you can think of it as a parameter or the X value of the machine learning model, which is a function. Yeah, it's synonymous with parameter. So when you heard that 175 billion parameter GPT-3, then those were 175 billion features. A label I mentioned earlier was the Y value of the machine learning model function, and it's the value that we want to predict. I don't know how they chose these names. They seemed a bit strange, but yeah, feature makes more sense than label to me. But some Azure concepts that are relevant to training the model that I'm sure being an Azure group you guys are familiar with. I'll just go over what we will have. You have to have a subscription, obviously, and a resource group. A subscription is the billing entity Azure uses to group things for payment, and the resource group is a logical entity used to group resources, usually by product or however you want to slice it, environment, common properties between them. The workspace is the ML Studio itself, and it's an Azure resource itself. The region is the operating region, like Central US or Eastern US. There is a way when you create the ML Studio resource to piggyback off of a previously created storage account, Key Vault, Application Insights, and Container Registry. But if they haven't been created, then as a part of the ML Studio creation process, it'll spin one up for you. And if you're not familiar with the storage account, it's a resource that has underneath it several different storage types that you can create. Key Vault is a key value pair secrets storage area. It's another resource, and the Application Insights is a telemetry and logging platform that you can attach to different resources and get out of the box a lot of logging without having to create it. And a container registry is a place to store your containers for your inference pipeline. So we'll move on to the next. Compute targets. So you have largely two types of compute targets that we're going to be using. I'll just go through what these four are because you'll see them. But a compute instance is a development workstation that data scientists or anyone who's tweaking any of these things can use to work with the data and the models. A compute cluster, they're scalable. The cluster of virtual machines for on-demand processing of experimental code. The inference cluster, we won't use that. Typically, you would use that for a production environment. Their deployment targets for predictive services that use your trained models. So they'll have RESTful endpoints and utilize the power of the scalable cluster. An attached compute is a link to an existing Azure compute resource, such as a virtual machine or Azure Databricks cluster. So you can take whatever ML Studio offers and make like a linked service to something external to ML Studio. And what we'll be using is a standard DS11 V2 VM image. It has 2 virtual CPUs, 14 gigabytes of RAM, 28 gigabytes of temporary storage, and it's about 15 cents an hour with pay-as-you-go. The reason we're doing this is because it's the best balance of cost and performance. More powerful machine would cost more, and less powerful may not work. But if you ran this 24 hours a day, it would about 30 days, it'd be about $107 a month. So, and that's the value that I wouldn't want to, as a single person trying to figure this stuff out, I wouldn't want to leave it on all the time. So I would turn it off. And we'll cover that at the end, like how to clean these things up. So what you get with this is it's a VM size. And it may not be one of these 4, but it may not be any particular one of these, but it will be one of these 4. And it will run on either premium SSD or an ultra disk, which is their highest quality, Azure's highest quality storage, persistent storage. And it's an SSD. It's usually used for IO intensive workloads, and it has a huge maximum disk size of 65,000 gigabytes, basically. So has a lot of flexibility there. So this is what the Azure Machine Learning Studio home looks like, and it's its own portal with an isolated view. It doesn't have the typical blade view that you see with Azure. There isn't a breadcrumb trail to go back to it, and we'll open it up here at the end after the deck. On the side, you can see there's 3 major groupings. We'll go over these after this. I'll just read through them here. Author, assets, and manage. Author, you can create things. Assets are your, all of your assets. There's your data sets, your experiments, pipelines, models, and endpoints. There's a flow to that. Typically, before you create your model, you're going to add in data. You're going to get it from a data source. You can add it in manually, and then you run an experiment on it, and then you create your pipeline. Your pipeline gets created from the experiment. Your model is generated from running the experiment, and then you take the model and expose it through an endpoint. So we'll also go over the compute section, and I think perhaps we'll also go over the environments. The data labeling and the link services we won't really speak about because that's not a part of the regression. So yeah, with the notebook, you work with files, folders, and Jupyter notebooks directly in the workspace, low code, more code solutions. If you want to be detailed, you can. You have access to all the workspace assets here, including experiment details, data sets, and models, and you can easily test your deployed inference pipelines with Python. With automated machine learning, it's the thing right below notebooks. It's a place where you can train and find the best model based upon your data without writing any code. It automates most of the process for you. The under the author section, the designer area, this is where you'll connect your database, your data set, perform cleanup and normalization, where you make all the data have like similar ranges of values. by changing the scale, and you can train your model. You can pull things off the shelf with the designer, pre-built, commonly used areas, and you can see previously created pipelines down here. With that view, it's similar once you click into anything on the pipelines area to the actual pipelines section. With data sets, self-explanatory. It's where your data sets are held, and it has detailed information about their character set, where they came from. Like, so you can see your data sources, URI, if it's from an external source, anything like that. Your experiments. So these are particular runs that you've done for your training pipeline. It's pretty self-explanatory. After you see what the flow of the sections under the assets is, this is where, our manually created or the automated machine learning experiment runs show up. Pipelines, you can be very detailed here, but it's the same view as what you saw under automated ML, and basically, it's lines and boxes. Think of it as input, output. So you can draw a line. Some of them have multiple outputs because you'd want to split or duplicate the, like you can read, it's kind of tiny here. The clean missing data, typically you would have common usage that they would have two different outputs from that. Models, that's where your trained models are. Assets and endpoints. On this page, you can create from scratch a deployed machine learning model. Real-time endpoints are endpoints that are used for real-time inferencing. Real-time endpoints contain deployments that are ready to receive data from clients and can send responses back in real time. So there are ways to do this as a singular RESTful request, but there's also batch processing that you can do here for larger data sets that would return at a later time. And under the compute section, compute instances respond to compute instances or where we are running our actual where we're running our Jupyter notebooks from. The compute clusters are that are responding to the requests that are happening from the Jupyter notebooks. Here's what we'll do. We're going to select and clean data. We'll train the model and we'll predict a new label. We'll use the historic data to train the model that predicts the value. And we're going to have this hypothetical business called Adventure Work Cycles. It's a bicycle rental shop that wants to use the historic data to train a model that predicts the demand of daily bike rentals. We can think of, as I mentioned earlier, the machine learning as a mathematical function that receives a series of values related to something, X, that are called features, and calculate a predicted label, the Y. And when we predict a new label, again, with features using the model, this is called regression. A bit about the training data. This is an image of it. This is the link to it if anyone was curious. It's open data from a company called Capital Bike Share. They have a license agreement with Microsoft. There are several data sets like this under the aka.ms. If you do a Google search, you can find the complete set of it that they've made available so people can play around with these things. It contains day of the week, month, year, and weather. So it's an association that people have. They believe that weather and season affects bicycle rental decisions, and it does. But there's missing parts to that because it's just a series of inferences that people are making.
Hey, Michael, you went on mute.
Oh, I hardware muted and then it didn't unmute. Thank you.
I can hear you.
Okay. So Yeah, when we run the inference pipeline, the value that'll come up for that top row, if we duplicate that, isn't exact to the historical data. Because there's some other missing parts to this. Usually a data scientist will take values and make some assumptions about how they're correlated together to come up with a way to predict the label. And there are some missing, like weather and season aren't the only factors that affect decisions for rentals, and reality itself is different from previous versions of reality. There's an infinite number of features that we could use to predict any one label. So, but as long as the errors are within a certain range, then it's good enough. Creating an Azure machine learning workspace. AZML helps to prepare the data and train the models and to publish the predictive services and monitor the usage of them. But it also helps with many of the time-consuming tasks that you see. So there's a lot of data formatting and normalization, excluding rows, removing empty values that might throw off the model with too much weight, or the implementation of the actual training algorithms can take a lot of time for somebody, but you could just pull them off the shelf inside the machine learning workspace. So, and now let's train and deploy a predictive model in Azure Machine Learning Studio. So this is the familiar view for Azure. You can get to the machine learning area from, I already have it here, but obviously, like if you want to create a resource or search at the bar, this is one that I've created earlier. I'll go ahead and create a new one inside of a previous resource group that I have and just give it a name. Let's call it December is almost over. You can see that it creates a storage account, Key Vault Application Insights, where I could select one that had been previously created. We're not going to create a container registry here. One will get created, though, at a subsequent step. So yeah, that's all that's necessary in order to create the thing. Okay, well, that's deploying. It shouldn't take too much time. In the meantime, I'll pull up for the next moment. Yeah, we can see if I think that's right. Oh, there we go. We'll launch the studio. Okay, so here's the view. We'll go through these real quick. Here are the notebooks where you would work with the files, the Jupyter notebooks, and create an empty one here. We'll use this one later. You can see it's like any other of the Jupyter notebooks that you encounter. There's automated machine learning for the codeless techniques to train the model. Here is the designer where you connect your data set, do the cleanup and normalization, and train the model. This is where your data sets are stored. Your experiments, where a particular run of a training model, either manually created or for automated ML, would show up. your pipelines, where you can dig into and flesh out your training and inference pipelines. It's the same as the view from the designer down here. Once you click into one, your models, this is where your resultant models are housed. From here, you can deploy an endpoint, or you could create the endpoint manually down here at endpoints. So you have the flow there. Compute, this is where you create your compute instances, clusters, inference clusters, and attached compute, which are, the external VMs or resources. And data stores, we won't be using that right now, but you can see, like, if you were to delete your endpoints and turn off your compute resources, then there's a small fee that would still be incurred from the storage of any of these things. So if you really wanted to wipe it clean after you've deleted your endpoints and shut down your compute for playing around with it, you would just delete the machine learning studio, and you double check like your storage account instead of Azure portal to make sure. But data labeling, you can have human mediated or like set up labeling projects for, let's say, images, and link services. There's some interesting stuff with that. You can link it to Azure Synapse Analytics. But let's move on. We'll go ahead and create the compute resources to train and test our model. Let's see here. We're going to, on the compute instances, setup, I'll call this llama drama. And we'll set that compute type that we mentioned earlier, the DS11. And we'll go ahead and create that. And while that's being created, we'll create our compute cluster. Central US, dedicated CPU. We'll also use a DS11 for that, V2. Compute name, we'll call this Madagascar. And set the maximum number of nodes to 220 seconds for idle seconds before scale down. That's acceptable. And we don't want to do SSH access right now, just for our purposes. Okay. So while that's running, do we have any responses to that question that was asked earlier inside of the presentation?
Just a couple. I was one of the guys who responded. I was like natural language processing. Mike said conditional access.
All right, could you say that again? Sorry.
I'm saying there were only a couple of responses. Mike. One was natural language processing. The other one was conditional access.
Like conditional access to apps based upon like some sort of interpretation of like biometric data or something like that, or
I think Mike is referring to Azure AD.
Oh, I see. Yeah, okay, gotcha. Yeah, natural language processing. I'm hoping for a lot more coming up with that. Okay, let's see. So while that's creating, I'm gonna go ahead. It might take a sec. Sometimes things like that take a while. Not too long though. The actual training of the model would take about 30 minutes, but I have a casserole in the oven, so to speak, over here, so we don't have to wait that long for that bit. But I'll go ahead and create the data set from the web files here. Data set name, we'll call this bike rentals. It's tabular and what's called sickle rental data. And we won't skip the data validation. That's part of the strength of this model type. I think it's it's k-fold cross validation, where they hold back some of the data in order to some of the data, the features in the training of the model, so that when it's testing itself, it already knows what a predicted label for that is, and then it helps to train the model. Okay, we'll move on to the next section. It's parsing the dataset info. It's delimited, comma delimited, UTF-8. We only want the first file has headers, and we won't skip any rows. There is no multi-line data. Okay, the schema, we want to exclude, the path. The rest of these, you can see how it's determined the data type here, and there's some examples. All of this is good. Checking it over. Yep. Okay. And we don't want to profile the data set after creation. That comes up with like common patterns from this one data set that you can use to correlate with other patterns from other data sets, but we're not going to be doing any of that. Okay, once that's done, it take us a few seconds for that to be listed. Okay, so you can see now our compute instance is running, the cluster succeeded. Now we will train our machine learning model by running an automated machine learning experiment. So we're going to do a new automated run from this data set that we just added. Let's call this gregarious goat. Our target column is the rentals. So we want to predict the number of rentals that the bike company should expect for any one day based upon the weather and the season. And we're doing the compute cluster. We're selecting the Madagascar compute cluster that we just created. And we're going to be doing a regression where we predict the numeric value. We're going to do the normalized root mean squared error, which I'll explain in a little bit here. And we want to only, the reason you would want to block an algorithm is because it's going to try to run all of these to come up with whichever one was the most successful with a lower error threshold using this metric. And we don't want to run all of these. It would take hours. It's honestly going to take long enough for us to do just two, but we'll do some of the smaller ones, the light GBM and the random forest. Those, they are more memory conscious and don't take as long. We don't want those to be blocked though, but we'll just select all these. This has been an issue with the user interface, it seems, the past week. I'll just save it and go back in. We can check the exit criterion, see training job time in hours. Let's put it at a half hour and put the metric score threshold to 0.08. And that's the maximum number of concurrent iterations happening on the cluster, because that's the maximum number of nodes that we have. So I'll just save that. View the futurization settings, it's enabled. Yep. Feature selection identifies the actions performed on the data set to prepare the data for training. Yep. Okay. Validation type auto, test data set. There's no additional test data set that we're using because we're doing the k-fold validation. Okay. It'll start automatically, but you can see here in a little bit, it'll start going through phases. Once the automated ML has been started, it'll one by one using that compute resource that we created, start running through the algorithms. And there's only two, but it really will take quite a while. So I'll just leave this running in the background and move over to, close this one, the pre-created. This is another Machine Learning Studio resource that already has some completed runs inside of it. Right now we're going to review the best model. So on this run, it randomly adds some words into the name of the run. You can see the algorithm name, the light GBM, was the more successful out of them. Hyperparameters are parameters that you use to tweak the actual run itself, but it aren't parameters that are being used to predict the label. Normalized root mean squared error for this one is below the threshold, so that's good. And yeah, the best model is identified by the normalized root mean squared error. It's a metric that's used. This is how it works. Like the training process held back some of the data to train the model and cross-validated it to test iteratively. The trained model with data it wasn't trained with, like I mentioned earlier, and it compares the predicted value that you saw with the actual known value. The difference between the predicted and actual value is known as a residual value, and it indicates the amount of error in the model. The normalized root mean squared error metric is calculated by squaring those errors or residuals and then averaging or finding the mean of the squares and then taking the square root of that. So the smaller that value is, the more accurately the model is predicting things. So within this area, there's a way to dig into it some more, like with additional graphs to see like the predicted line against the actuals, but we don't have to go into that right now. So yeah, this is the model, and you can see yeah, the metrics, explanations. From the screen, we can make a deployment. We don't have to manually create the thing down here. I'll go back to that. We'll deploy the model as a service, and it'll be a predictive web service right here. Call this rentals final presentation prediction. And we'll use a Azure container instance. In the machine learning resource, you can deploy a service as an Azure container instance or to Azure Kubernetes service cluster. Like I mentioned earlier, for production, you'd want to use an AKS cluster for the inference cluster, but we'll just use the ACI, no inference cluster necessary. Enable authentication. That way we can hit the thing in our notebook. This is all good. Okay, go ahead and deploy. Now, sometimes this can take a while, so I do already have an endpoint created right here, the predict rentals, so we can proceed with, now we can test our deployed service. We'll just use the predict rentals one, and we'll go to our notebook, and let's say we, oh wait, let me do this differently, because I want to be able to, yeah, I want to keep this open so I can copy that. I'll duplicate the tab. We'll create the notebook in the second tab. And we'll overwrite if it exists. Under, close this over. We want to make sure that we're using, that compute instance. Okay, things look good. If you haven't seen Jupyter before, it's you can even, most of the time I see it like interjected on like a blog post where they have code kind of like Stack Overflow, and then on the side you can execute the code and pass values between instances of the notebook so that you can demonstrate and speak about the code at the same time, but it's like a small IDE inside the browser here. Okay, so let me get this. This is some test Python here that we'll use to hit that endpoint. We'll just replace these two values, the endpoint and the key. The primary key. Okay, and we'll go ahead and save it. Did it save? Okay, good. And if all is well, looks like our compute is running. Cluster's good. The endpoint is healthy. Okay. We should be able to execute and get our predicted values. So there's 6 days here because we passed in, move up, 6 different sets of features representing 6 different days. And you can see here, we predicted 352 for day 6. I copied that last set of features for that day from this top row, so we could demonstrate that it was predicting fairly close to the actual number of rentals. 331 was the historical data, and 352 was the predicted value for the number of rentals for that bicycle shop. And there you have it. So we have 6 days of data that we could, with fair amount of confidence, based upon that normalized root mean squared error, should be a close approximation to what the actual number of bike rentals would be for that bicycle shop. So yeah, just to recap, we use the data set of historical bike rental data to train the model, and the model predicts the label of the number of bicycle rentals expected on a given day based upon seasonal and weather features. And that's all that one has to do in order to set up a regression model. Obviously, like some parts of this were already set up for us. There's the data collection and getting good data is and cleaning it up. It's usually something that requires a lot of work, but for the actual linear regression setup, you can see it really doesn't take that much time at all. So. I had my final slide here, but yep, that's the presentation, folks. Does anyone have any questions about that?
Feel free to unmute yourself if you have any questions or comments for Michael. If not, I guess on behalf of the user group, Michael, I'd like to thank you for taking time out for presenting today. And if there is no other questions, anything anyone wants to discuss anything, then I think we can wrap up. And since this is our last meeting for the year, I wish everyone happy holidays and thank you so much for joining us tonight. We'll be having our meeting from January. We are planning to cut down on frequency. So far, we have been doing twice a month. So starting January, we'll be having once a month. But with that, thank you once again.